Morning. We're now in Switzerland. We're at Cern now. So Cern, this place, what's got the Hadron Collider, which I'm going to be closed down in the next month or so. The Hadron Collider is, I think they're going to build something bigger or something else is going on. There is a route you can cycle around, but it's too far for us today to do that. We haven't really got the time, but we're going to have a look around here. It's more about science and innovation and things like that. I'll take a quick look at this up here. Don't know what language we're going to get. You're standing in front of a facility. It belongs to CERN. Use the passport to the Big Bang to find out what's behind these walls and all about that. So basically it's going to tell us about it. So that's part of like what's the Hadron Collider. And this is, it's 27 kilometers, so we're around here somewhere, and that there is a Hadron Collider. And I think what they do is they send atoms each way and they smash into each other, and it was supposed to be something to do with the Big Bang, trying to find out about how the world came to being. But I think they've got all the information and everything that they can get from that, so we'll just here to possibly learn a little bit more. We'll see. I think here's some of the maths for working 2012 CERN's Higgs boson. So how cool is that? So
I'm not going there.
I think it's all different things to do with physics and science and reading different things and learning for the world and that.
Quantum physics.
Quantum physics. Cool. I think they would act as like, what? It's copper, isn't it? Which is, as we know, one of the best conductors of electricity. Actually, gold is better, but it's a little bit more expensive. So this is part of the first accelerator, and I think what they do is they get the atoms from hydrogen and then they pass it through, so it's like a series of magnets, so it just gets faster and faster and faster. And I think what they do is ultimately they fire in the opposite direction, just the same, and then as it speeds up, eventually they crash them together and they take readings from it. And I don't know how they use the information, that's what it is. But copper will be, because copper is a great conductor of electricity and things like that. So, accelerating and colliding with particles. Okay, the magnets that they actually use to send it all the way around are some of the most powerful magnets on Earth. They need those so they can fire them at speed. This particle detectors use trackers to measure the trajectory of the particles produced in collisions. Knowing the trajectory of a particle is key to identifying it. Try out a tracker used in one of the LHC experiments. So, the stack of tubes on your left is a very, very enlarged model of the tracker. So they must be the new ones. One of the 4 large detectors to record the collision produces 0.25mm. There's 10,000 kilometres of them. This model is made up of layers of transparent tubes. Tubes facing towards you are identified by a letter. The tubes transverse are identified by a number. An additional layer of tubes arranged 45 degree angles. So that's them. When a charged particle passes a scintillating fibre, a small amount of light is created in the fibre and transports the end of the fibre. It's the same in this model. The tube lights up as particles pass through it. Things like that, say like on B, two, 3, 4. You don't see any on the bottom. So the structure in the middle of the table allows you to create the trajectory of particles. Each layer corresponds. With the letters and numbers arranged in the same way, each layer of the intersection between the column indicated. So, okay. So we've got B, so B2, B3, which is there, and B4, which is B4. So those ones, are incorrect.
What was that saying?
No, it's just telling you how they track in the particles of each one. So they've kind of simplified it. So you'd read it off here, look, B2, B3, B4. So I give you 2, 3 and 4. And then it's got A, B, C, D. And I can't see a light for any of the ones on the bottom. So there's nothing that's running onto there. Yeah, it's the thing about starting the experiment. Not very easy, to be quite honest.
Yeah.
Sorun değil mi?
Look at the two sides.
Both ways makes it go. That's a little. So I'm watching it. Don't waste it.
Alright, so you kind of follow it as it goes through like that. So the yellow there, and that runs up onto there. The red that's up at the top there. And there. So this is, if you look through it, that's what it actually is, but it's been made in glass. That's firing the particles, and that's where the collision is. Pardon? Yeah. That's firing the particles. That's the collision. There. And this is. That's tracking it. Don't really know what that is.
Sen de şu an şimdi korkuyorsun falan gözükmüyor.
Abi biz mi çok zekiyiz bunlar için? Bence kaldıralım.
Or and gates, or gates and no gates. Remember that from physics?
Right, yeah. Logic gates, and gates, or not.
Yeah, you need that and that to get that one. That's that or that to get that one, and that's not to get that one.
Okay.
For that, you need that an and gate. You need that and that for that to work. On this one, for that to work, you need that or
Like
that,
Yeah.
and that is not. If you don't have that, that'll work. That's your gates.
Don't get it.
When you're doing your circuits.
Oh, look at all that. What do they remind you of?
Tapes,
Yeah,
DVD tapes.
yeah.
Backup tapes.
Yeah. They're collecting information.
Sadece deney yaklaşıyoruz.
That's kind of what happens, look. It just fires them round, so I think the idea is you press that one. And, or maybe you don't. Oh, you need 4 or 5 people pressing them all at once. Yeah.
That's cool.
Yeah, it's bending the beam with a magnet. That pushes it along.
Faut qu'à midi vous ayez une vue globale et
And that pulls it.
That's really cool.
Okay.
Moves them round.
Yeah. That reminds me of, we used to have a game and there was iron filings in
Yes.
this game.
Yes.
And it had it like a glass
And you
top
can move
and you
it.
rubbed
Yeah,
it.
yeah.
And it created an electrostatic thing, and you could
Yeah.
move the metal.
Yeah.
Yeah, you could move the metal around to create like a beard and things like that. Centre connections.
Wow, minus 271 degrees centigrade.
Eh?
And the camera.
And the magnets are cold. That's absolute zero, that, isn't it? I think so, yeah. I should look that up, Christine, if I were you.
Ahí, quieta. No, no están mirando la cámara. No, está para allí, no para allí. Ahí, ¿has mirado más a la izquierda? Ahí.
¿Qué parece que otra? ¿Qué ha pasado? No, tenía que hacer.
Hecho así, y luego le he dado.
Y no hace nada.
Esto es un mando.
Ya, pero no que hacer nada.
No es una cámara. También me digo, anda que no sabes lo que es una cámara si quieres una bola esa. ¿Qué? Yo, pues, ¿por qué? Mira esto, por favor. Da mucho decir de mí misma que eres muy
Pero es que es mona. Hablar es algo mono. Ya ves. Vas a ayudar. Yo sé ni puedo hacer. ¿Ves?
So you're aware this is what's going on 100 metres below our feet. You've got this thing here, and you've got a beam of protons, essentially going this way. And you've got another beam of protons. And that's and then these are all just the magnets that keep the positive charge, they'll fly apart. So this is here to all these magnets just they keep it focused. But it has to be really, really cold. So it's all cooled by liquid helium. But 27 kilometers over our feet.
Si la trayectoria es muy pequeña, yendo tanto,
Yeah,
que sea exagerado. Cuanto más diámetro tenga, cuanto más grande sea, que no es necesario que el movimiento sea tanto.
It's a, you
Estamos
know,
hablando de
if you get a
ya con un diámetro de 25, es una fuerte.
Oh, that's why it's weird. It doesn't go fully in. On the end of it.
where's the end?
I'll look at you. No.
All right.
Yeah, I've got you both
This
moving
is all
out.
radioactive, so you can't go down there.
I'm following you along. Turn around. Oh, don't look. Stay there. And look at the camera. Why?
So if you get an apprenticeship there, they pay 40 grand a year tax.
On camera. Oh my god, Emma, I've zoomed in on your face.
It's a 2-year apprenticeship. It's a 2-year apprenticeship at 40 grand a year tax. Yeah, it's very good. They want all kinds of people. They teach you a bit more. But you pay for it first. So your tax. So very finely that you get that. The tax fee every year will go to. You pay about
You
four.
paid for me to take pictures of your
So for about it costs you about £4 a year on a real tax. And you will go through
That's positive news.
Yeah, but how much tax? So £4.
So your average tax payment, your average tax payment.
So I can pay like £2.
Yeah. They say it's a couple of copies a year, but then there's also loads of customers will go to us.
So we basically bought
Your scholarship.
So Rob, welcome. This is ELISA. It's the experimental LINAC for surface analysis. It's actually a fully functional proton accelerator. So I can actually, I can stand downstream of the proton beam and not die because the energy is about 10 million times lower than the big machine, okay? Although there is, like I said, some high voltage stuff, so do be careful not to go past here. So over here you can see there's like a nice pink colour, yeah? That pink colour is hydrogen. So the hydrogen is coming into the machine. We break apart the hydrogen into protons and shove the protons into this copper chamber here. So this copper chamber is called an RFQ, a radio frequency quadrupole. It sounds really complicated. It's basically just a piece of really precisely machined copper, okay? So what happens is, over here, this pulse is made 750 million times a second. It goes down like that. And it gets fed into this barrel thing over here. This barrel thing is called a radio frequency amplifier. It's kind of like, you know, a guitar amplifier, it's kind of like that. Amplifies up the power, feeds it through here, and then we tune the frequency. In the same way, you know, you tune a musical instrument, yeah? We tune our accelerator. We know that it's tuned because the red line is flat. When it's tuned correctly, it makes really strong electric fields. The protons come in, they see that, and they get accelerated really quickly. In the space of a meter, they get accelerated up to 2 MeV, 2 million electron volts, which is like a meaningless physicist unit of measurement of energy. But in real terms, it's about 6% speed of light per proton. Okay, so like tens of thousands of kilometers a second. Do you guys know what G-force is? Yeah? No? What's the typical G-force of a roller coaster? Any guess?
Is it
10 will be quite a lot, yeah? It's like 2 or 3, you know? So what, remember, like maybe you thought 10, like 9.8 is like 1 G, and then how many G's is like how many times is that, yeah? So what about a fighter pilot? So Tom Cruise in Top Gun, what does he get? Anyone know? Because he's doing a big turn. How many G's? Yeah, about 7 to 9, something like that. Can anyone guess or tell me how many G's does a proton feel as it goes through his machine? No one ever guesses it right. We've only ever had one guess, correct? How many G's, yeah? Way higher, way higher.
1 million.
still way off. It's about 4.5 quadrillion, so very high.
Wow.
This is actually one of the highest acceleration gradient machines that operates on Earth right now. So it's pretty cool to think about. This little machine is one of the fastest things that mankind can accelerate a bit of material at speed. It's actually quite a lot higher acceleration gradient than the big machine in the ground. So the big machine has a higher terminal speed or energy, but this machine has a higher amount of acceleration per distance. Can anyone think, like, why is that? Kind of seems weird. Why does this machine need to have a higher acceleration per distance? It's a simple answer. Smaller, so it needs to get more done. Also, the big machine on the ground is what? A circle. So you can actually reuse the same piece of accelerator, right? So it actually takes the big machine on the ground about 20 minutes to bring the beam up to energy, whereas this has like a microsecond or something. So why I was saying, if you're interested, you should come down this side, is because if you have a good eyesight and your eyes are just in low light, you should be able to see a very faint purple beam coming out of the machine. Can you see it? Yeah? If you're struggling, you can see through the phone, it's a bit easier to see, right? Yeah? So I'm going to put this on to be safe, just because this will protect my hand from the beam. I'll be a terrible doctor, so it's on. Okay, so can anyone tell me what's the main gas do you think that's causing this purple colour in the air?
Hydrogen.
Not hydrogen. Yeah, good guess. What's the main gas in the air?
Oxygen.
Second most. What's the most common? Nitrogen. Nitrogen. Yeah, exactly. So no, it's nitrogen. Nitrogen. Okay, I don't know what's in Spanish. So it's the same colour. You know, if you see lightning, you see this nice purple colour. It's the same process. So what I'm going to do now is I'm going to feed through some helium. So you know helium is what we put in balloons. Yeah, makes your voice high pitch. So helium it's a different gas. It's also much lighter than air. Okay, so it's going to change how the beam looks in two ways. Can anyone tell me how will the beam change as I feed through the helium? Colour, that's one of them. What's the other one? The other one's a bit harder to think about. So it's a lighter gas. So you're a proton going along, and now you're bumping into something that's lighter.
Pressure.
Huh?
Pressure.
Pressure is about the same. So it's actually going to go further, okay? Because you're now bumping into something that's lighter, so it goes further. Okay? That makes sense? The colour is in theory different, but in practice it actually has a similar colour by chance. You can also come down here, you can see there's a very nice parabola, just there. That's actually because the air is sinking down. See it? Now, the cool part about this is it shows something called the Bragg effect. So, naively, where do you think all the energy is being deposited in the beam? At the start, the end, the middle?
Yeah.
You're all physicists. That's the non-obvious answer, right? You'd expect, or at least I would expect naively, it to kind of go off like that, right? It should kind of start off strong and then fade away. Okay? But maybe because it's here, actually most of the energy is deposited at the end. So if you plotted a graph, it would kind of go bam like that. And it really does look like this, which is really weird. Or at least, if you don't think it's not weird, you're not appreciating what's going on. Instead of being, the protons kind of travel and then bam, they deposit their energy at a distance. Actually, if you look really carefully, squint your eye, it is actually a bit brighter at the end. And it's actually because imagine also because it's spreading out. If you're able to focus down the beam, you would see that it's brighter at the end of the beam, which is really strange. Okay. So, can anyone tell me what might this be really useful for? We have a machine which can use physics to deposit energy at a distance. What might this be really useful for? In medicine, in particular. I'll give you a hint. Imagine the beam is coming here. What might it be useful for? So someone said? No? So imagine you have a tumour in the middle of your head. Hopefully none of you ever do. But how would we get rid of the tumour? We would try and cut it out, it's kind of hard. No, a laser would just hit the skin, right? Another thing you try and use is similar to a laser, you try and use light. Okay? So you try and send in high energy photons of light. And they have a profile like this, where for every 1 unit of energy you get that reaches the tumour, you put 10 units of energy in the healthy tissue, which is not so good, right? Protons, because its effect is the other way around. For every 10 units of energy you put in the tumour, you only put 1 unit of energy in the healthy tissue in between. So you can deliver a way higher dose to the cancer, kill the cancer without damaging the healthy tissue, which is crazy. Okay? Now, the machines that do this, they're called cyclotrons. They were developed at Cern in the 40s and 50s. Do you think the physicists back then, when they were developing these machines, do you think they were thinking, this is going to treat cancer for children in 70th time? No. So this is a sales pitch, obviously I'm biased. When people come in, they're like, why do you spend all this money on useless research? We should spend money anyway because it's interesting, we should want to know how the world works. But also, like, you don't know what a particle accelerator is going to be used for in like 70 years time, right? Because it's a particle accelerator, right? It's by definition like cutting edge technology. So that's why we should give Cern like $1 gajillion. Anyway, so this machine is too low energy to treat tumours with, typically the 100 to 200 MeV. There's only 2 MeV. So what do we use this machine for? We actually use it for archaeology normally. So we work at various museums and they bring in scrolls, coins, cave paintings, you get the idea. And we use this very machine here to analyse them, to determine, you know, how old are they, where are they from, are they real or fake, did it come from this place, stuff like this, right? So actually, has anyone got any jewellery? They want to see what it's made of? If so, we can. Yeah? Yeah, let's test it. I'm going to take that one off. Thank you. Okay, very nice. So how this would go.
Okay.
Great.
Okay.
So what happens is the protons come in and they excite the surface of the material. They cause it to emit X-rays. This camera picks up the X-rays, okay? Now every different element will have like a different set of X-rays. Thank you very much. It's like a fingerprint, it's unique to the element, and so it allows you to identify which elements are present on the surface of the material, okay? So, let's see what it is. So let's see gold, right? Let's hope it's gold. Gold, there you go. Wow. So, there'll probably also be some copper. Yeah, so copper and gold. Okay, so normally there's like a copper band, and then gold on top, and then the copper kind of diffuses up to the surface over time. So it is real, don't worry. There you go. But you can see, so last question. There's all the methods that let you identify like what stuff is made of, right? So there's chemicals, gas chromatography. What do you think is the benefit of using this fancy machine? Because this costs like $1 billion. Why go to all the effort to use this really fancy machine to see what stuff is made of? What's the benefit, do you think, for priceless artifacts? So other methods require you to chip a piece off, right? Take a little sample. This doesn't, it's completely non-destructive. It doesn't damage the sample in any way. Obviously, if there's like a priceless painting, you don't want to have to chip a piece off all the time. This is completely non-destructive, your ring is totally fine. And so it's obviously really useful for archaeology. Yeah? So anyway, if anyone has any questions about how any of this works or any of the questions of Cern, I'm happy to answer, as is my colleague outside. Otherwise, thanks for listening. I apologise it's so hot. It's quite annoying. But yeah, otherwise, thanks for listening. If you have any questions, answer. Otherwise, free to go and have a good day.
Oh, sorry.
We'll change it to that.
So there's the galaxy. Sun and planets. Build your own star. You need hydrogen, helium, here's gas in the star's fuel. How much do you want to use? Choose a quantity in 0.5 and 50 times the mass of the sun.
Next.
If you wish, you can add a pinch of heavier atoms. These are made by a previously generated star, then scattered across the universe. Okay.
It's cool, that.
In the universe, everything spins. Give your star a spin and discover the life it will have. If the universe is spins, observe the evolution of your star. There's the star. Send it out into the universe. Watch the wall in front of you. You'll see a star. And those made by others. So,
There is.
there is look.
How cool is that?
That's quite good, that one.
Very good, that, yeah.
Finished.
That's really good.
Excuse me. Let's see. Oh.
Was that the thumb?
Go on, you can if you want.
Yeah. Sorry. Thank you. Not easy, are they? Can't in between. Can't in between that.
No, can't in the bottom, isn't it? So that wall there is the earliest image of the universe, and they're microwaves. Before there were any stars or galaxies. That's infinity, isn't it? I think something to do with infinity.
It's nice, doesn't it?
Because there's no start and there's no end, is there?
Yeah.
Corona 7 is a large knotted form inspired by the connections between space, energy and matter. It consists of 324 cells made of transparent polymers that constantly change colour and pattern when friction and pressure are applied each kinetic movement. These cells undergo subtle changes reflecting the fluxes in our universe, producing a never-changing spectacle. It says, as you observe Chroma 7, what do you notice? More than an optical change of light and colour. Kim's artwork, oh, sorry, I was talking about his image. Oh right, yeah, it's just got like balloon lights on it in the minute. Oh. Very strange place. It's about a quantum world, so it's explore how the universe works at tiny scale, exploring the infinite small me, encountering some strange behaviour. The laws of physics are very different to the ones we're familiar with on a human scale. In the world of particles, uncertainty rules. A particle moves several places at once, even the most unlikely events occur, and two particles can influence each other instantly across vast distances. These are the laws of quantum physics. Such phenomena can only be perceived at the scale of atoms and molecules, but they have very real consequences in our daily life. Quantum physics explains why the sun shines. It allows us to make smartphones and understand how plants grow. Yeah.
I give you the headset. You just need to follow the group. You can turn it on and you score the visual. Okay. You have no time to do this part, so you can do it.
No, you haven't got time.
You are in shrinking, imperceptibly becoming smaller and smaller, a million billion times smaller than at the beginning.
Right, electrons. Don't waste time. Well, I think that's the end. Not got a clue.
About the Casimir effect.
You're recording, man.
Eh?
You're recording.
Alright, Emma. That was a Casimir effect. Something to do with bending light through. When there's a vacuum. Okay? Okay, we're going to go have a look at this in two parts. The first part is the old bits and pieces, how it all came about in the first place. Then we're going to go back over the other side and have a look at where they are and what they're up to now. So, just a bit of a tour that we've got to have a look behind the scenes. You can't go down and have a look at the Hadron Collider. It's forbidden for the public to go down there.
It's not fair, that.
But it's, they're super magnets and things, so
Yeah.
parts of it can be radioactive and all sorts.
Première institution supranationale, c'est l'Europe qui commence à tuer. Les règles.
In 1949, Europe recovers from World War II. Many eminent scientists have left for the United States. European research is no longer world class. To reconstruct European science, the visionary French physicist and Nobel Prize winner Louis de Broglie proposes the creation of a European laboratory that would be both a centre of excellence in physics and a motor for peace. His idea is taken up by American Nobel Prize winner Isidore Rabi, who together with Pierre Auger and Eduardo Amaldi convinced UNESCO to adopt this process. 18 months later, 12 European nations formally agreed to create the Conseil Européen pour la Recherche Nucléaire. The acronym Cern is born. Important decisions are taken in the first sessions of the new council. Geneva is chosen as the seat because of its central location in Europe and its international tradition. Two accelerators are put forward, the synchrocyclotron and a much larger machine, the proton synchrotron. A new convention defines Cern's goals, stating that its research will have no concern with military requirements, and that all its results should be made public. The Cern Convention is signed by 12 nations. Among the signatories are eminent physicists such as Werner Heisenberg. Cern comes into existence. 1954. On a site in Meyrin, a small village near Geneva, work for the new laboratory begins. Within a year, the farmland is transformed into a large complex of workshops, offices and buildings to house the new accelerators. The 5-meter thick walls of the synchrocyclotron building soon emerge, while the different parts of the new accelerators are manufactured in several European countries. The synchrocyclotron's magnet coils require particular care to pass through some of the Swiss villages on their way to Meyrin. As components arrive, they are assembled with great precision. Everything starts to take shape. The synchrocyclotron emerges, piece by piece. Some 54 elements are put together for the magnet frame. A total of 2,500 tons of steel. Next, the two 7.2 meter diameter magnet coils are installed. With a current of 1,800 amps, they generate a magnetic field of 2 Tesla. The rectangular vacuum chamber is fixed inside the magnet. A system of large vacuum pumps is installed to evacuate the 25 cubic meter chamber so that protons can circulate unimpeded. This is followed by the installation of 2 D-shaped electrodes inside the vacuum chamber. Together with these electrodes, a radio frequency generator creates the electric fields. That accelerate protons from a source inserted in the center of the vacuum chamber. In summer 1957, the synchrocyclotron is ready, and Cern's first accelerator comes to life. The purpose of the synchrocyclotron is to produce and study new particles. Before accelerators were available, such particles could only be observed in cosmic ray experiments. The new machine accelerates protons to 80% the speed of light, producing millions of new particles when those protons collide with a target, giving scientists the opportunity to make systematic measurements. Operation of the ESC requires a sequence of actions. Massive pumps extract the air from the vacuum chamber so that protons do not collide with gas molecules during their acceleration. In the proton source, hydrogen gas is ionized and a cloud of protons is injected into the middle of the synchrocyclotron. The accelerator makes use of magnetic and electric fields. The magnetic field is produced by a current of 1,800 amps flowing through the coils of the huge magnet. 2 D-shaped electrodes with opposite polarity are fixed inside the vacuum chamber in the middle of the magnet. Protons have a positive charge and are drawn towards the negative electrode as they traverse the gap between the electrodes. The magnetic field forces them to follow a circular trajectory, and they return to the gap after 1/2 turn. Meanwhile, the radio frequency generator reverses the polarity between the 2 electrodes. The protons are now attracted to the opposite electrode, and gain more energy. This process is repeated over and over again. Every time the protons make a half turn, they are whipped around faster and the radius of their path increases. After more than 100,000 turns, they have reached an energy of 600 million electron volts and move at 80% of the speed of light. They are now close to hitting the target, and the first experiment can begin. In 1957, young scientists from all over Europe arrive. Among them are Maria and Giuseppe Filiparo. Giuseppe wants to study a short-lived particle called the pion. In 1957, there was a mystery surrounding the pion. Theory predicted that a direct decay into an electron and a neutrino should happen, but this had never been observed.
Phenomenology of this process. Only later on in 1957, when with the theory of Riemann-Husserl theory, the problem really had some kind of solid theoretical basis. So at the moment, the absence of the pi decay was very critical. It was essentially a block for the physics to go through. It was really felt like a block. And was at that time, in January 1958, that I thought that was the right moment to do this type of experiment.
Giuseppe and his team set up a clever experiment. The pions are stocked in an apparatus designed to study their subsequent decay. In 1958, only a few hours after they start the experiment, the first pictures show clear evidence for this rare decay.
I can imagine. I was really excited, and surprised. Can't describe. I mean, it was something essential because something I was seeing something for the first time. I had seen before.
This first important discovery spread Cern's name around the world. Over the following years, scientists at the SC continued to make many important measurements on particles, atoms, and nuclei. 1967, a new idea takes shape called Isolde, an isotope separation device. Protons from the synchrocyclotron collide with target nuclei that are split into short-lived fragments, which are then rapidly scrutinized in experiments. The study of such short-lived nuclei with too many or too few neutrons helps to understand how heavy elements are produced in exploding stars. The synchrocyclotron accelerates its last beams in December 1990. After 33 years of an exceptionally long and successful career, the SC is retired.
Well, we felt that the synchrocyclotron had worked very well, much more longer, and even it was much more than anybody ever expected, because he renewed in the field of physics, explored the 33 years. He passed, explored many different fields, and has been very useful.
Following the synchrocyclotron's construction, Cern built bigger and bigger accelerators. The proton synchrotron, the intersecting storage rings, the superproton synchrotron, the large electron-positron collider, and the Large Hadron Collider. Many important achievements were made, some of them being rewarded with the Nobel Prize. The drift chamber, which revolutionized particle detection. The cooling of particle beams. The discovery of the carriers of the weak interaction. And the Higgs boson, which proves the existence of the Brout-Englert Higgs field. In 1989, Tim Berners-Lee, while working at Cern, created the World Wide Web, which has since changed our world forever. The Large Hadron Collider will continue to run at higher energy and higher intensity, with more than 11,000 scientists from over 100 nationalities, hoping for new insights into the secrets of the universe.
I think that the curiosity and the need to do research is inside is a part of our humanity. So there will be always a Cern. So there will be certainly future.
What started once as a vision for European science has grown into a unique model for global scientific and technological collaboration. Cern demonstrates how science can unite nations and contribute to a better world.
A detector from 1950s. So this is the detector from which we get an idea to make a bigger ring of 27 kilometers, which is about the size of 3 to 4 villages under the Swiss and the French border. So we have started from this wheel kind of small ring. Our actual ring in this experiment is inside this wheel. So from this wheel, which is in one building, we have extended our experiment to bigger ring of 27 kilometers, which is covering 3 villages under Switzerland and France. So right now we are at the mega village of Switzerland, and here nearby we have the point 1 of the machine, which we are going to visit into the next part. But the other points of the machine, they are lying on the front side in the Saint-Denis village of France, and also in the Cizé village of France, and then it come back again to the mega village of Switzerland. So this is our starting point, and we have extended our experiment with an effort of 50 years working over it into a very bigger ring of 27 kilometers. So here we have the velocity of our particles, which are called as proton, which is about 80% of speed of light, and in the new experiment it is 97% of speed of light. So in order to obtain this much gain in velocity, we must shift from a few centimeters to 27 kilometers, so that our particles have enough path to travel up to a very high velocity as compared to what we have now. So in this building we have about 2 minutes left. You can take pictures and videos, and after 2 minutes we will leave the room and ahead to the next part. Thank you.
Yeah, there's some of the eminent physicists looking. I suppose that's some of the mathematical equations behind it all, which means absolutely nothing to me. Anyway, we're off on to the next part now, so that's kind of about how it all started. And right, we're going now.
So exactly below 93 meters of that building, we have the same detector, but bigger in more than 2 times of this size. And we have the elevator in this building, which can land in the underground at different floors of the detector, like -1, -2, -3. And it is about the size of like a 5 to 8 story building, and we have the -1 floors into the underground. And there is no other way to go into the underground, only the elevator is present that are taking us to the detector. So before going to the other side, I will ask you to stop into the next ground, into the shade area, and I will go inside to check the availability of the room, and after that I will ask you to enter to the main building. Thank you.
That's only a portion of the size of how it really be.
I know. It's mad, isn't it?
Mm-hmm. This is Atlas.
This is Atlas.
Where they collide and take the.
Yeah.
So please wait in this area, and I will ask you later to come inside.
Okay.
There. Oi.
This experiment. Meanwhile, the other group will be outside, and then we can enter to the control room area. So the control room is at the back, at your back over this side, and we will see it from inside to that room through the window. It is not allowed to enter into the room because it is a place for the scientists and the shifters to work there and record data with the Atlas experiment. So here at Cern, our purpose is to find out the fundamental building blocks of the matter so that we can understand matter in a better way. So at one time we came to know that the atom is the smallest piece of the matter and there is nothing inside. But later, with the help of experiments, we came to know that inside atom we have electrons, protons and neutrons. And then here we are colliding proton beams and we want to know what is inside protons. And we came to know that when two protons are colliding, they are gonna break into smaller particles, which are called as quarks. So our purpose is to scan matter that we have find out inside atom there are electrons, protons and neutrons, and inside protons and neutrons there are quarks, and inside quarks there must be other particles, and inside them the other and other particles. So our goal is to reach to the smallest or the basic building blocks so that we can reach to the composition of the matter effectively. If we are able to find out the building blocks of matter, we will be able to describe our matter in a better way, and our whole universe is made up of matter. So we will be able to understand our universe in a very, very good manner. So we can tell what has happened with this matter a long time ago at the time of the Big Bang, and what is gonna happen in future. We want to predict the Big Crunch. So this is our goal, to understand the matter so that we can understand our universe effectively. So at Cern, in the underground Large Hadron Collider, 27 kilometers of the ring, we are creating the conditions that are nearly close to the Big Bang, and the conditions are high temperature and high energy. So we are providing much and much high energy as much as we can to our proton beams, and we are colliding that protons at that much of high energy so that it is much close to the Big Bang, and we wanna see after two protons being collide at that conditions which particles they are gonna break. So we want to see what were the particles present at the time of the Big Bang. So mainly our concern is related to energy. So in the first detector that you have visited into the first part, we have about the 80% of speed of light that we have given to our beam, and here we are operating at 97% of speed of light with a center of mass energy of about 13.6 tera electron volt, which is about the energy or the for this process we are consuming electricity equal to 1/3 of the Geneva city. So this much of energy we are providing to our beams so that we can see what are the particles at that much high energy or high temperature. So this is about the LHC experiment. So at Atlas we have discovered our goal for which this tunnel was made up. So we reached to the the God particle of the proposed standard model in 2012, which is called as Higgs boson. So that was first predicted in 1973 by the theory group, and in parallel from 1950s we have learned a lot from our old detector, and then we decided to make a bigger machine in 1992. We have signed the model of this Cern Large Hadron Collider in 1992, and then we reached to our goal in 2012. So it is a journey from 1957 until 2012 that we find out that Higgs particle. So in this way we are assuming that if we are able to achieve the experimental conditions that are nearly close to the Big Bang, or maybe sometimes exactly close, we cannot say now we are nearly close to the that high temperature or high energy conditions. So if we are able to achieve these conditions as effectively as we can, and we can then look into the proposed parameters being proposed by the theory side, then we are able to get the particles that are missing from our model of the standard model of the particle physics. So here our goal is just to scan the matter and to find out particles so that we can understand our universe in an effective way. So at LHC ring, in order to do this kind of stuff, we have about 4 detectors. So this is one of the biggest general purpose detector, the Atlas experiment, and the other biggest and the general purpose is over the other side of the ring, right 180-degree opposite to this area, which lie in this is the village of the France, which is called as the CMS detector, a compact one. And with the help of these two detectors, we are doing the general discoveries, like discovering the general particles, like the Higgs boson, which we got in 2012. And then we have the other two specific purposes detectors over this machine. So we see the new particles in two detectors, and the other two are dedicated to measure the properties of already discovered particles. So we operate in a way that we have built up a 27 kilometer of the ring, and we have placed two general purpose detector, and we have placed two specific purpose detectors. So these are the 4 points over the area of that 27 kilometers. Then there are 4 other points of the machine which are not the detecting units. They are just to go into the underground for the various other measurements. And I, as a working as a physicist, I cannot tell you more about the points that are not related to physics measurements. So I am mainly focusing the detecting stuff that we are doing here. So in the Atlas experiment, you will see inside the control room, there are many desks at which the people are sitting day and night, 24/7 when the beam is in operation. So right now we are in the last week of the proton-proton collisions, which is gonna end this week. We are gonna in the shutdown state, and we completely shut down on 29th of June 2026 after 4 years of operation of the data taking. So right now there must not be many people because we are going to shut down, but when the beam is in operation, the people are present 24/7 because our detector, our machine is running all the time, and we need to record the data continuously. So we have divided the shifts in a manner of 8-hour shifts for the 24 hours. So the first shifter comes in the morning at 7 o'clock, and then they leave at about 3 o'clock in the afternoon. And the second shifter is from 3 p.m. until 11 p.m. and the third is from 11 p.m. until 7 a.m. in the morning, 8-hour duty of the night hours. So we have divided our 24 hours in this way that the shifters are present here all the time. Then we are responsible here to record the data effectively and to send our member and associate member states. So we have started with 125 associate and full members, and the now number is more than 130. So here the original data is generated, which is called as the tier 0, and we make the first and second copies of that data, and we are responsible to send it up to the countries all around the world that are linked with the Atlas collaboration, so that the people sitting in their country can also take advantage of that data and can contribute towards the physics analysis, like the measurement of the new particles. And after 5 years, we make that data public, but within 5 years it is confidential under the Atlas collaboration. Only the Atlas members can log in or can access that data. Then same goes for the other detectors in the CMS side, in the LHCb and in the Alice detectors. So they have also their own privacy policy where they have to send data, how many copies they want to make and what they want to do to public it after 5 years or whatever they want. So mainly this field is for searching physics, but here the people from all areas are present. So here we have people from physics, which is the main field, the particle physics, but the people from material science, which is an interdisciplinary field from physics, are also present. There are people from mathematics, we have people from computer science, because the artificial intelligences and the machine learning techniques are being dominated in this era. So all the fields are working for physics, but they are, it is not like everyone is coming from the physics background. So all the fields are working in a way that we are contributing towards the physics measurements. So I think it's 4 o'clock, we can enter the room. I will check one time more and then I will take you inside.
This is CNN Breaking News.
Bonsoir à tous et bienvenue.
Bienvenue dans ce 1930. Bonsoir à tous dans l'actualité de ce mardi.
Physicists at the Large Hadron Collider in Geneva.
Día los medios de comunicación destacaron el descubrimiento de Peter Higgs.
The significance and the excitement over the Higgs boson part.
Implies that the Higgs boson takes us to the instant of creation itself.
And it stands with the great scientific discoveries of all time.
One big spike here, in this region here. So, zooming in this region.
Well, I would like to add my congratulations to everybody involved in this tremendous achievement. For me, it's really an incredible thing that has happened in my lifetime.
The discovery of the Higgs boson was a key moment for science. The Higgs boson is a quantum ripple in a universal energy field that gives particles their mass. It was the last missing piece of the Standard Model. This model describes the basic building blocks that make up the world around us. By studying these particles and their interactions, scientists are learning about the structure and fate of our universe. The ATLAS experiment was built for just that purpose. It sits 100 meters beneath your feet on the Large Hadron Collider, or LHC. This is the most powerful particle accelerator in the world, bringing protons and ions nearly to the speed of light before smashing them together at the heart of ATLAS. Physicists then record what happens during these collisions, looking for signs of new particles or interactions. To see the smallest particles of the universe, you need enormous detectors. The ATLAS experiment is a complex machine the size of a 10-story apartment building, and it took over a decade to construct. It is made up of several layers of detectors, each designed to study different properties of particles. Monitoring this complex experiment and analyzing the data is a global collaboration of scientists. With research teams on every populated continent, the ATLAS collaboration is one of the largest scientific efforts ever accomplished. Whether they are at Cern or at a research institute abroad, ATLAS members work together to analyze LHC data, operate the experiment, and even construct new detector pieces. Discovering the Higgs boson was just the beginning. From the smallest particles of light to the heaviest quarks, ATLAS scientists are studying the fundamental constituents of matter to better understand the rules behind their behavior. These measurements and discoveries have advanced our collective knowledge of the universe. While our understanding of the subatomic world has advanced rapidly over the past decades, there is still a lot left to discover. The Standard Model describes ordinary matter, but that only accounts for 5% of the known universe. The rest is made up of dark matter and dark energy. But what exactly are they? ATLAS researchers are looking for new particles and forces that could explain these mysteries. As scientists work to unravel the mysteries of the universe, they are also advancing technologies that change lives. From the World Wide Web to proton therapy, fundamental physics research has already had an impact on your everyday life. Where can it take us next?
Okay, so you have seen some important clips from the discovery of the Higgs boson 2012, which we made to discover about half a century. Starting from 1957, in 2012 we got the Higgs boson. So after this video, if you want to have a look at the control room, you can move towards the other side. And here at a distance of just 1 light window, we have the control room managing about 93 meters underground detector. So this is the control room from which we are managing the underground detector. So here there are many computers and desks which are now empty because we are in the shutdown stage about to approach on 29th of June. So when the beam is in operation, then there are many people in this room and monitoring all the parameters that we have over the wall. So here mostly desks belong to the inner detecting units. So each and every desk here is responsible to monitor each and every part of the underground detector in all of the area except the middle one. So in the middle area we have some general desks like the desk of the shift leader. So shift leader is like the leader of the full room, and he and she has to take a good decision at the right time in the data recording. And then we have the run control system here. So here it is just a matter of clicking one big red button, start button, and we are able to start the run in the 93 meters underground detector over a 27-kilometer ring, and the detector size is about size of 8-story building. So just a matter of one click that we can start the run in that kind of big experiment. But after the run is started, it takes about 20 minutes to reach to the stable conditions. And as we have the stable beams, then we can trust our data and we can put it on recording. And that data after recording can make or convert it into different copies and can be used here or sent into the different countries all around the world, linked with the Atlas collaboration. So of course, this clicking over red button is not easy. We have worked years and years over it. Starting from 1950s, and now we are able to set up this technology, and we are able to start or stop our machine with the matter of one click from one of the desks here in the middle. Okay, so we have discussed mostly stuff outside, and you can take pictures and videos if you want. And meanwhile, you can also ask me any question if you have over the Atlas experiment. So just the last one last sentence that we are in future, our future project, the FCC, which is called as Future Circular Collider, it is much more bigger than 27 kilometers. So 27 kilometers is about 3 villages in this area with 97% of speed of light in the with the proton beams. So our new project, we are building a detector much more bigger than this one. We are trying to operate 99.9% of speed of light, and for this we require the ring of not 27 kilometer, we require about 91 kilometers of the ring, and we are planning to make that ring under the Geneva Lake, and we have to sign the model of our next machine in 2050. So we have, in this time, we are working over this project, and until 2050, we will search all the physics and science, how we are going to build that much of the big experiment, and we are going to sign the model of the machine at 2050, or maybe 10 or 20 years later is also possible, because our field has a much more longer time for the construction and for developing the technology. So maybe our next generation can work over the future project, but we are now limited to this 27 kilometer. Okay, that's all. You have again 2 minutes to take pictures. It's called as now shutdown. That will do all the details and updates of the pictures. And after 3 years,
That's quite interesting. There's a piece of it. And it's got Lego, doesn't it?
It is Lego. I'd love to
the things are progressing rapidly and then so the maintenance is really done into the long shutdown, but due to some unfortunate reason it is happening, some leakage or something, because then of course we need to there. Part of the Atlas detector is a part of LSC. Is a part. So it is one of the biggest detectors. There are other detectors who have seen.
It's quite cool,
Higgs boson is discovered by 2 detectors, Atlas and CMS.